moment generating function of x. The moment generating function of a random variable x is defined to be this, okay? I use, and I think your book uses, little m, okay? The function is called little m of t, okay? It's a function of t, okay? This thing is, it's supported over some region of the real line that includes 0. And sometimes we'll put a little x down here, or a big X down here in the subscript to denote that we're talking about the moment generating function of the random variable x. Okay? It's defined to be the expected value of e raised to the power of t times x. Okay? We say that the moment generating function exists if it is finite everywhere on an open interval that surrounds 0. Okay? All right, so it turns out, by the way, before we go any further, that there are many useful generating functions or transforms of random variables. We're going to primarily work with moment generating functions, but you should be aware of the fact that there are others. They're characteristic functions. By the way, the characteristic function of a random variable is sometimes we give it the symbol phi or phi, not fo or fum, but phi or phi of x. It's defined to be the expected value of e to the itx. It's essentially the Fourier transform of the probability mass function or the density function. But regardless, if you write this out as an integral or a summation, you'll see that it looks like the Fourier transform. This always exists. Always exists. Okay? The moment generating function doesn't always exist. There are, in fact, random variables out there that don't have moment generating functions that exist because they don't. There's no open interval that surrounds 0 where this thing is finite. But sometimes we prefer to work with these over characteristic functions. There are others too, like Laplace transforms. Laplace transforms. Okay. Maybe we'll denote it like that. That's just defined to be the expected value of e to the negative tx. Okay, so if I swap t for negative t in the generating function, in the moment generating function, I get a Laplace transform. Okay, and these always exist for non-negative random variables. Okay, so they can come in usefulness of them is good for us. Okay. And there are others. Your book talks about probability generating functions. Again, we are going to focus, at least for now, on moment generating functions. So the utility of these things, the utility of moment generating functions. Number one, they completely rule. That is, they completely characterize their distributions. Okay, that is, in theory at least, if you have a moment generating function, then from that you can get everything you want to know about the random variable itself. You can calculate probabilities, you can calculate means, etc., etc. They also generate moments. Who would have thought? The moment generating functions generate the moments. That is, if you have it, if you have a moment generating function, you can very easily get the expected value of x, the expected value of x squared, the expected value of x to the 99th power, etc., etc. And we'll see how to do that in just a minute.